Okay, here I'm going to be walking through a solution to a problem in which we have to prove that something is a vector space. Before I read out the actual question statement, let's do a bit of review first. First of all, if you have two sets A and B, then their symmetric difference, this little triangle symbol is used for it, is one of these two definitions. These are equivalent definitions. You can either think of it as the union minus the intersection, or as the union of each of the sets minus each other. So we can visualize this with a Venn diagram as such. The two purple shaded regions here together form a symmetric difference B. You can think of it like the elements that are in either of A or B, but not both. Okay, next thing to review is the field F2. So this field has two elements in it. It's a set containing 0 and 1 with little brackets around them. And on this set, we have addition and multiplication defined as such. So in its barest form, this is just addition and multiplication mod 2. Okay, so this is what the problem statement says. Let M equal the set containing the digits 1 through 9 ones each, and as usual, denote by P of M the power set of M, a set whose elements are all possible subsets of M. Okay, now we're going to introduce two functions. This one, little circle around a plus sign, I will be pronouncing it as O plus. And it's defined on the Cartesian product of the power set of M with itself to itself, and another function, which I'm just going to call star, which is the field cross the power set to the powers. So we will define the O plus to just be the symmetric difference, and since F2 has two elements in it, these two equations define star. When you do 0 star, you get the empty set, and when you do 1 star, you get the set itself. So these will take the place of vector addition and scalar multiplication. The goal of this problem is to prove that such triple forms a vector space over F2. And in order to prove that something is a vector space, you have to show that all of the axioms for a vector space hold. So the axioms for a vector space, there are different ways to list out the axioms for a vector space. I'm going to go with this particular way of listing out the axioms for a vector space. So this proof boils down to just verifying that these 8 things are true. Okay, so miscellaneous properties of the interactions between the addition multiplication in the field and the addition multiplication in the vector space. 3 of these axioms in particular begin with the phrase there exists. So proving there exists means you have to find an example of something that satisfies that property. For the additive identity, 0 in that power set, you might guess that the additive identity would be, say, the empty set itself, or the set M itself. For axiom 4, the additive inverse, you might guess that the additive inverse of any subset of M would be the complement of that set in M, or the set itself. And for the multiplicative identity, there are only 2 elements in F2 to choose from. Likely it'll be the case that 1 is our multiplicative identity. Okay, and one final note before we get started here. The fact that M is the set containing the digits 1 to 9 is completely irrelevant. The proof that I will be showing you here actually works for any set M, not just this one in particular. Okay, so I'm actually going to skip Axiom 1 for now, and I'll do that one at the end. So let's do the last 7 first, and then we'll come back to this one. Okay, so another whiteboard now, just to remind you, these are the axioms for a vector space. I just copy and pasted that over from the previous board, but we're not going to focus on axiom 1 for now. So let's start with axiom 2. Axiom 2, we want to show that O plus is commutative. Or in other words, for every 2 elements of the power set of M, A O plus B equals B O plus A. Okay, and the key to showing that this holds comes from the fact that the union is also commutative. Okay, so a lot of these proofs are going to begin with the left side one of those equations and ending with the right side of one of those equations. And I'll just replace O plus with symmetric difference because that's what it's defined to be. This is the definition of the symmetric difference, and now the key here is to note that since the union is commutative, these two things can get switched. And now this is the exact form of B symmetric difference A, which is BO plus A. And that verifies axiom 2. For axiom 3, we need to show that there's an additive identity. So on the previous board, I said that additive identity could be perhaps the empty set or M itself. You can trial and error it, and you'll find that the empty set works as an additive identity for this, what we're going to show is a vector space. That just comes from the fact that when you do the symmetric difference with the empty set, you end up doing that set itself union the empty set, which leads you right back to that original set. So the left side here equals the right side, and that verifies axiom 3. And a lot of the rest of these axioms, I'll be coming back to axiom 3 and using it a lot. Just remember that whenever you do the symmetric difference with the empty set, it gets you right back to the set itself. So in axiom 4, for example, to find the additive inverse of any set, I mentioned a good guess could be its complement or the set itself. The complement seems like the more obvious answer, but it actually is not the additive inverse of an element in this vector space. The additive inverse of any set or subset of M is itself. And that comes from the fact that when you do symmetric difference of a set with itself, you end up doing the empty set union the empty set, also the empty set, which is that additive identity we found from axiom 3. Okay, so that verifies axiom 4. Axiom 5, you'll notice, has alpha and betas in it. So alpha and beta come from the field F2, which means there's 4 different possible combinations of values for alpha and beta. So this axiom requires these 4 lines to verify. And you go through and verify these lines on your own. The key to this part of the proof is to remember that the empty set is the same thing as 0 star any other set, and it's also the same thing as 1 star itself. The only one worth noting here is this last one, where you don't end up doing 0 star anything, but all the 1 stars sort of go away because, as we will see in the next axiom, axiom 6, 1 is actually a multiplicative identity for this vector space. So this one's actually really straightforward. 1 is our multiplicative identity just because the definition of star said that when you do 1 star any other set, you get the same set that you started with. So that verifies axioms 5 and 6. Let's go on to 7 now. 7 has an alpha in it, no beta, so there's only 2 different values of alpha to check. I did this in the backwards order just so I could fit things on the screen here, but you'll notice that when you do the 0 star version of this axiom, you end up using the fact that the empty set is an additive identity from axiom 3. And the 1 star version is very straightforward because 1 star anything is itself. Okay, and finally with axiom 8, this is the hardest of these 7. The distributivity of star to the plus, this is the plus with the field F2, not the version of addition in this vector space, which is our O plus. Okay, so this is axiom 8. You just do all of those combinations of alpha and beta with zeros and ones. You'll end up using axiom 3 a lot just to turn any set into that set O plus the empty set. In this second line here, we actually needed to use axiom 2, the commutativity, just to get the zeros and the ones in the right spot. And in this last case here, you actually end up using axiom 4 instead, which uses the fact that any element is its own additive inverse. Okay, that is all of the last 7 axioms. Let's talk about this first one now. This one deserves its own whiteboard. So this is what the actual proof of axiom 1 looks like. It's just a one-liner. You just replace the O plus with the symmetric difference, and you use the fact that the symmetric difference is associative, and then turn the triangles back into O pluses, and you're done. This step here is the one that requires more justification. It seems like just a simple set equality, but verifying that these two sets are equal to each other is extremely non-trivial. So if we can show that this symmetric difference associativity holds, then we're done. That gives us axiom 1, and we can conclude that the given thing was a vector space. But it is non-trivial. If you want to go about proving this directly, it'll look a little something like this. So that is absolutely disgusting. Let's just pretend like we never saw that, and instead let's justify it using a Venn diagram. Before I show these Venn diagrams, let's talk about the rules for shading these Venn diagrams first. When you want to calculate x symmetric difference y, so x and y are just placeholders for any other set, you want to shade in every region that is in exactly one of x and y. Another way of saying that is you want to shade every region that is in x or y, but not both. So in this whiteboard here, that's what happened. These two purple regions, these are the regions that are in A or B, but not both. And this just comes from the fact that the symmetric difference can also be realized by this other definition, the union minus the intersection. So it's in one or the other, but not both. So if we take a look at B symmetric difference C, it'll look a little something like this. The blue region is B symmetric difference C, so dark blue, and A is in this pink circle here. So just focusing on the left side of this equation, we want to shade all of the regions that are in the pink circle or the blue regions, but not both. Okay, so these two regions here are marked with red X's. Those are the regions that the pink circle and the blue shaded regions have in common. And there are 6 check marks in green in these 6 regions. And those are all the regions that are in A or B symmetric difference C. So we want to shade all 6 of these checkmark regions except for the ones that have red X's in them, because those are the regions that A and B symmetric difference C share. If you do that, it'll end up looking a little something like this, where you have shaded in each of only the A, B, and C and the one smack dab in the middle. So this is pretty symmetric in A, B, and C, hence the name symmetric difference. And if we do this the other way using the same logic, we'll find that we get the exact same shaded region. The only difference this time is we are looking at the right-hand side of this equation, where we start with asymmetric difference B, and then we shade all the regions that are in the pink circle C, or the blue shaded region in dark blue, and not in both of them. Okay, so that's like a visual way of justifying why the symmetric difference is associative, but that tells us that O plus is associative, which then tells us that all of these axioms for this vector space hold. Therefore, this triple, the power set of M, O plus, and star, is a vector space over F2.